Good morning, dear students. I welcome all of you in my class. Today I am going to teach you exercise 1.1 of Unit 1 real numbers. This is very important exercise from the board point of view. So let's start. In this exercise I am going to use Euclid division lemma, which I already taught you in the previous sessions. Okay, now I'm going to some quick revision for you. Euclid division lemma is A is equal to BQ plus R. 0 is less than equal to R and less than equal to B. Here A is dividend, B is divisor, Q is quotient and R is remainder. Let's start with the first question. Use Euclid division algorithm to find the HCF. Here everyone know what is the meaning of algorithm. Algorithm is a stepwise procedure. In this question we have to write the solutions stepwise. Okay, first of all I have number 135 and 225. 225 is greater than 135. So in the side rough work I am going to perform a HCF method for these two number. 225 divided by 135. 135, here I getting the quotient 1, remainder 90. Since remainder not equal to 0, I am again performing this HCF for 135 and 90. 90 divided by 1, I am getting 90, remainder is 45. Again remainder not equal to 0. Again we use HCF for 45 and 90. Here quotient is 2 and remainder is equal to 0. And because our remainder comes to 0, so at this stage we stop our procedure. At that time the divisor is 45, so our HCF of these two number is 45. Now according to question I have to write these steps in a stepwise procedure, which is required in this question. Used Euclid's division algorithm. Okay, now I am going to write this. 225 is greater than 135. By using Euclid's division lemma, A is equal to BQ plus R. 0 is less than R, less than B. 225 is equal to 135 multiplied by 1 plus 90. Since remainder not equal to 0, so we again use Euclid division lemma for 135 and 90. 135 is equal to 90 into 1 plus 45 according to this lemma. Since remainder not equal to 0, again we use this procedure for 45 and 90. 90 is equal to 45 into 2 plus 0. Since remainder comes to 0, so we stop our procedure. At this stage the divisor is 45. Hence the HCF of 135 and 225 is 45. I hope you all are able to do the first question according to Euclid's division algorithm. First of you do to find HCF by this method. With the help of this you are able to write in the algorithm form. Now we come to the second question. Show that any positive odd integers in the form of 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integers. Let A be any positive integer and B is equal to 6. I am going to explain you one thing here. In the form of 6q plus 1, 6q plus 3, 6q plus 5, 6 in place of B, because lemma is A is equal to BQ plus R, so we let B is equal to 6 and put the value in our lemma. By putting the value in our lemma, we get A is equal to 6q plus R. 0 is less than equal to R, less than 6. Now the possible remainders of R is 0, 1, 2, 3, 4, not 6, because the sign is here less than 6. By putting the value in the star, 6q plus 1, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5. Everyone knows odd numbers are 1, 3, 5. Now I am selecting odd numbers 1, 3 and 5, because in the question we are given any positive odd integers. That's why I am selecting only odd cases 1, 3 and 5. So therefore any odd integer in the form of 6q plus 1 or 6q plus 2 or 6q plus 3. Okay. Now we come to the third question. Any army contingent of 16 members to march behind an army band of 32 members in a parade. The two groups are to march in the same numbers of columns. What is the maximum numbers of columns in which they can march? Maximum means highest factor. So here we have to only find the HCF by the same method in the first question, but there is no need to write a algorithm. We only write in the simple way. 616 is equal to 32 multiplied by 19 plus 8. Now we apply HCF for 32 and 8. 32 is written in the form 8 multiplied by form is equal to 0. Now the remainder is 0. At this stage the HCF is 8. Therefore the HCF of 6, 16 and 32 is 8. Hence the maximum number of column is 8. That is our answer. Okay. Now I am going to question number 4 and 5. These two questions are again very important questions. Okay. Use Euclid division lemma to show that the square, here we find the square of any positive integers is either of the form 3m or 3m plus 1 for some integer. In contrast, I am going to read the question number 5. The same question is here. Use Euclid division lemma to show that the cube, here the cube is given, here the square is given. The difference is that then in the form of 9m plus 1 or 9m plus 8. First of all let x be any positive integer in the form 3q plus 1 or 3q plus 2. Because here I am letting some different number, because when we do the square of number, it changes the formation. It changes the formation of equation. That's why I am letting some different number. Let x be the positive integer in the form of 3q plus 1 or 3q plus 1. The same letting part is here. Let x be the any positive integer in the form of 3q plus 1 or 3q plus 2. Here in this question, because I am going to doing the square of these numbers, so I am using the identity a plus b whole square, a square plus 2ab plus b square. Here because I am going to cube the number, so I am using the identity a plus b whole cube, a cube plus b cube plus 3a square b plus 3ab square. Okay, now I am taking the first number x is equal to 3q. On squaring both sides, I am getting 9q square, taking 3 common because I have to prove 3m. So I am taking 3 common. The rest value is known as m. Now I am taking the second part, 3q plus 1, by using identity a square plus b square plus 2ab. I am getting the value 9q square plus 6q plus 1. Now I am taking 3 common from these two numbers. The remaining part is known as m, where 3m plus 1. Okay, now I am taking the third part, 3q plus 2, by using identity again a square plus b square plus 2ab. I am getting 9q square plus 12q plus 4. But I want to take common 3 from that. That's why I am writing 4 in the form 3 plus 1. Taking 3 common from these three numbers, I am remaining left with 3q square plus 4q plus 1 plus 1. The bracket part is known as let to be the m. The number is 3m plus 1. Hence every positive integer in the form of 3m or 3m plus 1. Note here, 4 can be written in the form 3 plus 1 for taking common 3 from that number. Okay. Now I am going to the fifth question. The same part is here, but in this question I have to do the cube for numbers. First of all, I am taking 3 cube. By cubing I am getting 27q cube. But according to our question, I have to prove 9m plus 1, 9m plus 8. So I am taking 9 common here. The remaining part is let to be m. The number becomes 9m. Now taking second number, 3q plus 1. By again using the help of identity, I am expanding here. A cube plus b cube plus 3a square b plus 3ab square. I am getting these values. 27q cube plus 27q square plus 9q plus 1. On taking 9 common from all the numbers here, remaining left with 1, because 9 is not common taken from the 1. The bracket part is let to be the m, so the number is 9m plus 1. Again going to the third part, let x is equal to 3q plus 1. By using again identity, the same identity here, I am getting 27q cube plus 54q square plus 36q plus 8. 8 is not part into 9 plus something, so I am leaving 8 here as it is, but I am split 4, 3 plus 1 here. Okay, I am taking 9 common from that. The bracket part is let to be the m, 9m plus m, where m is number, hence our result, every cube of any positive integer is either in the form 3m, 9m, 9m plus 1 or 9m plus 8. I hope with my notes and with my video, it's proved very helpful for you to understanding exercise 1.1. I am repeating again, this is a very important exercise from the board point of view, to go through these questions and do in your notebook very neatly. Okay, thanks, have a nice day.